was republished. This edition was published in 2019. The author dedicated their book to their family. And then we have the contents. First, we have the foreword by Caroline Taggart. Then we have the introduction, and it starts with the science in general, in sections: physics, energy and electricity, generating electricity, heat transfer and efficiency, using electricity, forces, the four fundamental forces, planets, stars and galaxies, the origins of the universe, laws of physics, waves, radiation and space, waves, the electromagnetic spectrum, radioactive substances. We start here with chemistry, the periodic table, how the table works, atomic structure, chemical bonds, chemical reactions, collision theory and rates of reaction. Then we have views, air pollution, chemicals in the air, measuring pollutants, useful chemicals from crude oil, making life cycle assessments, metals, the earth's structure, metals and alloys, construction materials, organic chemistry, natural polymers and their roles in nature, nutrition, harmful chemicals. Then we have biology, human and other bodies, circulation, skeletal structure, muscles and the skin, nervous system, digestive system, reproductive system, respiratory system, sensory systems, cell biology, structure of a cell, photosynthesis, hormones, evolution and environment ecology, the origins of life, the evolution of the eukaryotic cell, mutation and natural selection, population, predation, extinction, genetics, and chromosomes. Then we have inheritance, reproduction, and cloning. Finally, it's the index and further reading. So we start with the foreword. Science was, I have to confess, far and away my worst subject at school. I remember only the oddest things, being dazzled by the beautiful blue of a copper sulfate solution and fooling around with a heap of iron fillings and a magnet. I knew that vitamin C, oranges for avoiding scurvy, and vitamin A, carrots, good for the eyesight, long before anyone had invented the concept of your 5 a also knew that the knee bone was connected to the thigh bone, but that was about as far as I got. That's why this book is so fascinating. Marianne Taylor has not only explained lots of topics that many of us may only have remembered or never really have understood, she has also expanded on things that are all around us, things that we take for granted but are a fundamental part of our lives on Earth. The air that we breathe, the electromagnetic waves, the power microwave ovens and X-ray machines, the way our genetic makeup turns us into the individuals that we are, those unimaginably small atoms that can be split to unleash devastating power. These are all elements, no pun intended, in that huge subject called general science. If you enjoyed science at school, this book will remind you why. If you didn't, it will show you what you have been missing and help you to catch up. And if you have some fun along the way, so much the better. So, let's start with the introduction. Most of us know there is fun to be had from science, as well as an immersive sense of achievement when you do finally grasp a tricky concept, but our experiences from school days may put us off trying, and we switch off our brains the moment things get too technical. School's finished, and there is no need to struggle with this stuff anymore, right? Well, when you leave school, you can indeed leave behind a lot of stuff you learned. You can go day after day, week after week, without needing to remember the names of the kings and queens of England, or the world's tallest mountain and longest rivers. You may never need to speak French or German in your life again, and if your command of written English goes downhill somewhat, it probably will go unnoticed by most. More's the pity. Science is different though. Science is everywhere. It muscles in on your day-to-day life, whether you want it or not. From deciding which vitamins you should take to working out how best to heat your home, it's all about scientific principles, and you have everything to gain and nothing to lose from familiarizing or refamiliarizing yourself with a bit of science. This book covers more or less the same stuff you'll find in an average school syllabus. However, we're not trying to get you through an exam, but to get you excited about science. The traditional three scientific subjects taught at school are physics, chemistry, and biology. When I was at school, they were taught as separate subjects, and you choose one, two, or all three. Most students today study combined science, which counts as a double GCSE, which might seem like a step in the wrong direction. However, it makes good sense on one level, in that separating out the sciences is difficult and actually not all that sensible, because there is much overlap in understanding aspects of one relies upon having a grasp of subjects of the others. I think I agree with that, because when someone is an engineer, he should understand physics, and when someone is a doctor, they should understand chemistry as well as biology, and in a way physics too, in my Physics is the study of fundamental forces and particles. Because it deals with things that we mostly can't see directly, there's a lot of theory and a lot of mathematics, and therefore it's the one science that people generally find the most daunting. Physics is sometimes considered the study of the very big and the very small, from universes and stars to subatomic particles. Once you have assembled enough subatomic particles to make an actual atom, you enter the realm of chemistry. This science deals with the properties and behavior of atoms and molecules, of the many and varied elements and compounds in various different settings, from the school lab to the blast furnace and the atmosphere of Earth to the insides of the cell in our bodies. And so chemistry surges effortlessly well, more or less, into biology, the study of living things from the molecular machines, I can't say that drive our internal processes. Biological study works up to the structure and organization of the cell, then onto the ways cells of different types are combined to form the body's various different systems, how those systems work, and finally from the individual organism to the ways populations and the whole ecosystems work. So here and there I may have said a bit more about some things and a bit less about others. Some of the concepts we're going to explore are difficult, but every year has been taken to explain stuff in straightforward language and to steer clear of unnecessary terminology, mind-bending mathematics, and overly esoteric subject matter. I kind of like this because I was reading this study. It was actually a paper about geology, and there was this incident years and years ago. I can't remember if it was thousands or hundreds. In Norway, the coastal continent started drifting into the ocean like a staircase that has a term for it, like this. And it kind of like started falling into the ocean, and that caused a tsunami. And I was trying to read the paper, and I came across so many unfamiliar terminology for me that I have spent more time trying to understand what each word meant by Googling everything I was reading, and then it took me to actually read the paper. So I like that it doesn't have complicated terminology because I'm not a scientist. I like science. I wish I paid more attention to it in school, but I wanted to pursue my study, and now that I finished, I started getting into science, and it's one of the most interesting subjects for me. I wish my teachers made it as interesting as some others make it seem. So, where were we? Again, esoteric subject matter. Wherever possible, diagrams and real-world examples are added to help make things more understandable. You may find after you've read the book that you're hankering after a bit more detail about certain topics. check out the further reading section at the end for ideas on where to go for more in-depth study. If the sciences didn't work the way they did, we wouldn't be here. I misread that, I apologize. If the sciences didn't work the way they do, we wouldn't be here. And being able to understand how science works is one of the best things about being human. Science and pseudoscience. Because it applies to everything in this book, this seems like the right place to explain that the scientific method, what the scientific method is and isn't. For science to work, it needs to be carried out with an honest and consistent method. The basic process is that a hypothesis, a possible explanation for a phenomenon is proposed. Then we come up with predictions that would fit that hypothesis and test the predictions to see if the hypothesis can be proven false. Pseudoscience covers things that look science-like but don't fit the scientific method. For example, we can't scientifically test the existence of God because the statement God exists can be falsified. We can put down any lack of evidence to supernatural explanations. God is omnipotent and can therefore choose to go undetected regardless of our searching methods. Pseudoscience also describe things which are claimed to be true but for which convincing evidence has not been found. So, we're starting with physics. Energy and electricity. Energy and electricity. Generating electricity. Electricity has to be up there as mankind's favorite energy source. It's easy to work with and we can use it to power all kinds of machines and processes. However, naturally occurring electricity is rare and unpredictable. Harnessing lightning strikes isn't really a practical option, for example. So we generate our electricity by converting other more easily obtainable energy sources. Natural energy sources. Our world is replete with many different potential sources of energy, which can convert into our preferred form, electricity. Some of them are sustainable. We can keep on using them indefinitely. Others aren't. We still use them up eventually and they won't get replaced. Let me have some water because I'm getting thirsty. Fossil fuels are coal, natural gas, and oil. They are called fossil fuels because they are the compressed remains of ancient forests, coal, or tiny sea animals, gas and oil squashed up and broken down into carbon-based compounds which burn readily, releasing heat. They are not sustainable because the conditions that produce them no longer exist. Also, burning them releases extra carbon dioxide and other unwelcome gases into the Earth's atmosphere, contributing to global warming. Despite that, about 75% of the electricity used in the UK comes from power stations that burn fossil fuels, though alternative sources are becoming more and more widely used. Nuclear power is generated by breaking up atoms of plutonium and uranium. When nuclei, I'm not sure how that's pronounced, of atoms from these two elements are battered with particles called neutrons, they release the heat energy. Inside the nuclear reactor of a nuclear power station, this process, nuclear fission, is initiated and controlled, and the energy harnessed. The process doesn't release toxic gases, but the waste it generates is dangerous. Nuclear fuel is non-sustainable, and an accident at a nuclear power station could have very far-reaching and disastrous consequences. Wind power is a sustainable source of energy. Large wind turbines, like giant futuristic windmills, are sited in exposed places with strong prevailing winds. The wind turns the turbine blades, and this kinetic moving energy is captured. No pollutants are produced, but wind farms can be unsightly, noisy, and dangerous to birds. If I can be honest, I find windmills fascinating, and even though many people find them unsightly, I actually find them beautiful. E equals mc squared. E equals mc squared. E equals mc squared. Bet you weren't expecting to see this quite so soon, but this most famous formula from Einstein's theory of special relativity and first proposed in 1905, I'm sorry, post, I thought I missed a word, is not as scary as you might think. However, it just means that matter, any kind of physical substance like rock, a star, a bar of chocolate, or your cat, and energy are different versions of the same thing. This comes into play in nuclear fission. The products of the fission reaction together weigh slightly less than the original fission material because the missing mass has been converted into energy. E equals energy. M equals mass measured in grams and kilograms. C, the speed of light, which is a constant. It doesn't change no matter what. The formula shows how much energy is stored in a quantity of matter. The main points to understand from this are A, matter is a kind of energy, and B, energy doesn't go anywhere. You can't add a new energy to the universe, and you can't take any away, but you can change it from one to another. What this has to do with generating electricity is that we can convert any form of energy into any other form of energy without losing any of it. Some of it might escape from our control, but if our energy converting machinery is well designed, we can keep this to a minimum. Water power is another sustainable energy source. Tidal barrages across estuaries capture. I'm sorry if I don't pronounce some things correctly. English isn't my first language, and if I don't, let me know in the comments. I don't mind the corrections. Energy as the tidal changes. I'm gonna start from the top. Tidal barrages across estuaries. Estuaries. Is that it? Capture kinetic energy as the tidal changes move water in and out of the river mouth. Hydroelectric power stations use dams built across rivers and capture the water's energy as it flows down pipes built into the dam. Neither produce pollution, but they damage wildlife habitats. Geothermal power stations capture the natural heat energy from volcanic areas. It is sustainable and does not produce pollutants, but is only available in a few places worldwide. Other energy sources include the solar power, wood, biofuels, oils derived from crops, which can be burned like fossil fuels, and hydrogen fuel cells. The energy sources used by country vary quite a bit. For example, UK 74% fossil fuels, 19% nuclear power, 1% hydroelectric power, the rest from other renewable sources or imported. I'm noticing that some sentences, I'm not sure if this was on purpose, but that sentence doesn't have a period in it. And that one doesn't have one either. That one doesn't, but that one does. Oh, that's interesting. Anyway, I wanted to say that I know maybe it's because this edition was printed last year, but I know the UK uses 20 or 21% nuclear power, and it has 15 nuclear stations. Not 19. Maybe I got it wrong, I don't know. The USA has 83.4 on fossil fuels, 8.5 nuclear power, the rest from renewable sources. Iceland, 74% geothermal power, the one we saw earlier with the volcanoes. 25% hydroelectric power and 1% fossil fuels. That's awesome. We use 87% fossil fuels worldwide, 6% nuclear power, 6% hydroelectric power, and 1% another. I don't know what that means. Does anyone, can you see? I hope it's focusing. But it's a capital A, a capital N space, and then space and other. If you could tell me what it means. Or maybe it was a typo. I don't think it was a typo, but expected these figures to have changed quite a bit in 50 years' time. Yeah, I know for a fact that they're closing down in 2025 a few of the nuclear reactors. I'm sorry if I don't really remember if it was new power plants or reactors or stations. So I know by 2025 some of them will be closed, or one of them at least. Whatever your source of energy, the process of converting it to electricity requires that the energy first be made into kinetic energy, and then that this kinetic energy is used to drive a generator to produce the electricity. In the case of wind and water power, the harnessed energy is kinetic already. With the others, heat energy must be converted to kinetic energy, usually by using the heat to turn water into steam, which then powers a turbine of some kind. The generator has an electric charge in its workings already, but it's the input of kinetic energy that causes the electric charge to flow. Let's move to heat transfer and efficiency. As I write, it's winter. It's winter time, and we've had some problems with the boiler. Moving heat energy around in the most efficient way possible is a major human precaution. And if we'd never learned how to do it, we wouldn't have been able to colonize such a large proportion of the available land surface on Earth. Heat has three ways of getting around: conduction, convection, and radiation. Conduction means traveling directly through matter, whether solid, liquid, or gas. If you hold a spoon over a candle flame, pretty soon you're going to want to drop the spoon because it's too hot. That's conduction. Some materials conduct heat better than others. The structure of metals make them good conductors, so we make radiators out of them. Convection is the movement of heat through liquids and gases. When you add extra hot water to your bath, the heated water expands. Or, to be precise, the space between the water molecules get bigger and the molecules start moving about more, becoming less dense and thus taking up more space. It rises above the more dense cooler water, which sinks. The rising of water, less dense liquids or gases, and falling of cooler and more dense liquids or gases produces convection currents. You might see birds of prey taking advantage of the rising hot air currents, thermals. Okay, I'm starting to figure out why this book was very cheap. I'm not sure if I'm not getting something, but here it says, you might see birds of prey taking advantage of the rising hot air currents, thermals. That what? Why is that? I mean, I get it. Don't put that over there, because it doesn't make sense. Maybe it does. Maybe I'm not getting it. I mean, it wouldn't be the first time that I'm not getting something, so maybe I'm just weird and everything's perfect. Thermodynamics. Time to lay down the law, or laws in this case. The movement of heat is governed by four physical laws, which are as follows, converted into sensible language. Thank you for that. The zeroth law. If two heat systems are both in equilibrium with a third, they are also in equilibrium with each other. The first law. In a closed system, the amount of heat remains constant. The second law. In a closed system, heat will always spread out as evenly as it can. Another way to put this is that its entropy or state of disorderliness disorderliness. I think they're synonyms. The third law: at the temperature absolute zero, the entropy of a system is zero. It's zeroth because it was added as an afterthought, being almost too obvious to be worth writing down. The second law is the one of interest here because it's what we're working against when we try to keep our homes warmer or cooler and the world around us. So it's been 40 minutes since I started this video. I will load the page for you, and I will make another one tomorrow, maybe after I finish work, because it's I don't know if you can see my watch, but it's 4 in the morning and I have to get up at 8:30 because I have a meeting at 9:30, and I had to give up a project today because I didn't think it was very interesting, but I'm just thinking of how to word it. Be patient with me. It was about a charity, and this charity is doing great. It's doing amazing work recently, but years ago they did something accidentally that it was unethical, and they didn't think of the consequences, and they've asked us for a way to present this, what happened in the past, in a positive way through a storyline. And I had to give it up because as I told people, it's not a good idea to talk about the charity, firstly because we're referencing something that happened in the past without us taking into consideration what the good things that the charity did. So it's like we're taking up things that they did in the past and we're attacking them now, which didn't seem very ethical and right. And I have a meeting tomorrow to discuss that, to avoid being misunderstood by accident.